All right. So we're in 6-4 today. It's the 20th. By the way, so what would we use? We're not going to reason all the way through this. What would we use to solve this got it? What information, what properties, what theorems? We're just going to cover these really quick and then dive into 6-4.
You know that CBA and PBM are congruent by vertical angles?
Okay, so we got vertical angles. So the first thing I see is that.
And then angle CE or CAC is parallel to MP. So
Because I see this in my given.
that means that angle C is equal to angle M by alternate interior angles.
Alternate interior.
And then same for A and P.
Alternate interior. Because yes, you do have to sing it. It doesn't work, no. Because I'm using different colors, I'm able to just use the one tick, but on your papers, if you're trying to show this, use multiple tick marks to show the different sizes of angle. Or, multiple arcs. So you could double arc it if you want. But just make sure that there's some kind of specificness. And from there, we've proved it using angle. And of course, we don't have to say the third angle because that's redundant, but you could. Now here, this one's a little bit hard to see on your printout. And this is actually one of the most useful applications of similar triangles. And we will try to apply this later in the year or maybe in the spring. But you can use similar triangles and a mirror to figure out an unknown height. So let's say we're out trying to figure out the height of a rock wall because we want to climb it. Now the dangerous thing about climbing is how much rope do you actually need? Twice the amount of what you're going to climb, right? So however far up we figure out we're going to climb, we need to make sure we have twice that much rope so we can get up and then back down safely. We could go up with only one length. We couldn't get back down.
You could jump. You just have more than you need.
Yeah, well, we want to have at least twice as much because otherwise we'll have to drop to the ground. And that would not be fun.
I think we did this project before, it was at Ohio Wesleyan Junior League.
Okay.
They had us take a mirror and they wanted us to find the length of this pillar.
Yeah.
And nobody knew how to
It
do
was an application of this.
Yeah, nobody knew how to do it.
Yep. So this is pretty famous, this method, because they were using this sort of method back before there was actual measurement. Back before there were ways to really quantify things, they would do things more as comparative of if I took this many steps, or if it's this many, what's the word I'm trying to think of? It was the measurement from the tip of your finger to your elbow.
Bingo bell.
I'll think of it in the middle of the night. But seriously, this was a measurement that you would buy things based off the person's size of that measurement. So if you saw that the person selling it had larger arms, you'd know their measurement would be slightly longer.
Don't buy it for me.
I forget what it
Don't
was.
buy it for me.
That's going to drive me crazy till I think of it. But this distance was seriously a measurement that they would say okay, this much, and then fold it, and then that much more, and that much more, and if you were buying fabric or something. So how do I know that these triangles are going to be similar? What is happening right around down in here? Ethan?
Angle.
So we've got angle, but why do we have angle? How do I know that those angles are congruent? Because if you can't see it, it's showing you that this angle is congruent to this angle.
And then there's two right angles. Well, there's one right angle and that angle and one right angle.
Right. So, but go back here. How do I know these are congruent? What property or mathematical principle lets me know those are congruent?
What?
How do I know these angles are congruent?
Oh.
It's not a very difficult question. It's probably seeming more difficult than it is. I'm probably asking it poorly. Brian?
Vertical?
They're not vertical because this line would continue through the ground and this line would continue through the ground.
The adjacent ones.
The what?
The adjacent
It's
ones.
not, they're not adjacent. They don't share a side. This goes back to billiards. I have a friend who's very, very good at billiards. And he's also very good at math.
Is that pool?
Billiards is pool. Is what playing pool, the pool table, it's billiards. Because a pool is the thing you swim in. So, on a billiards table, there's 9 pockets, or 6 pockets, right? 1, 2, 3, 4, 5, 6. There's either 9 balls or 18, or there's all different variations of pool. But when I want to hit the ball, let's say that's like right here, and get it to come this direction, I'm going to have to hit off the wall. So when I hit off the wall, what do I know about how the ball is going to come off the wall? If it's a proper pool table. I don't know if you ever played on a nice pool table or not.
I have.
So if let's say this is really, really acute. Let's say the ball's really close and I hit it like this. You know, I hit my ball like the cue ball this direction, it hits into this ball, knocks into the wall right here.
It's gonna bounce off like
the
this
same
way.
Why?
That's how like
Mirror should give, the word we're trying to get to starts with an R.
reflection.
It's an angle of reflection. So when you hit up against something that you know has certain properties, like a mirror reflects things exactly how if it's a correct mirror as opposed to like the wacky mirrors they have, but it will reflect at exactly the same angle that you came in at. But the part that people goof up is it has to be the same angle up against the same surface. So you have to make sure that if this wall was my surface, it's this angle that comes off of the surface. So if we're down here, the ground is my surface, so the angle coming down will be the same as the angle coming up. So based off the reflection angle, we know those are congruent, and then I see angle, angle, so I've got similar triangles. How does this bigger triangle relate to my smaller triangle? How can we figure that out? Is that a hand or no? Is it Carmen?
Because of the angle sum, or
we
triangle angle sum.
Well, we don't need to know the third angle. I don't really care how big the third angle is.
No, but I was saying because if since they have 2 angles, then 2 congruent angles, then the other has to be.
Yeah, so we've already said they are similar. We want to know how are they similar? What's the comparison? How do I go from one triangle to the next? Really, we're trying to figure out that unknown height. We need some number to get there. Caleb?
There's a relationship between 34 and 6. I think.
We know there's a relationship between 34 and 6. And the way that I know those sides relate is it's the side between my known angle at the ground and my right angle. So the side between my known angle at the ground and my right angle, these 2 sides relate to each other. Not that they're the same, but they relate to each other. So we can set up our similarity ratio. 34 over 6 will be the same as... so we could reduce this, but I have big triangle over small triangle, right? So Calvin, I should set up.
H over 5.5.
Yeah, just do your big triangle over small triangle. Set up a proportion that relates. Here are the sides that I know have to have this relationship. These have to follow because they are other corresponding parts. So if I cross multiply, Brian, do you have 34 times 5.5?
I can.
Well, I thought you just did that. You probably jumped right to the division.
187.
187
Yeah.
equals 6h, and then we divide that by 6. How tall is that wall? It's going to be like 31.
1.16 feet. I think. Wait. Yeah.
Yeah, because 1/6 is 0.16 repeating, just the 6 repeats.
Wait.
So I would need at least 62, a little over 62 feet of rope to climb that wall and make it back down safely. Yeah.
How do you know that height is the height of the wall?
How do I know this height or what?
That line.
This?
Yes.
So I chopped the picture off just because printing, I never wanted to print more ink than it has to. But there you can kind of see rock face right here, and you can see rock face right there. So this point is supposed to be the top of the rock face.
But like in practice.
Oh, so here's my mirror. I am looking at my mirror, walking back until I see in the mirror the top of the wall. And I know that my eyes, according to this image, this person's eyes are 5.5 feet up. So the height of their triangle is 5.5 feet. The hypotenuse is the line of sight. So then this line of sight reflects off the mirror to the very top of the rock, and I can figure out this distance from the mirror then corresponds to this distance from the mirror, and my height will correspond to the wall height. So it doesn't work if you don't see the top of the wall in the mirror. The only way we make the similar triangles is that my top point, my eyes would be my top point then, match the top point of the wall. And the similarity is made because the reflection angle and the right angle of I'm standing straight, and we talk about the altitude or the height as if it was vertical.
Wait, does H stand for height?
Yes.
Oh, I was so confused because there's an H variable in there, and I'm
Little h, that's why I use that. So
I'm
this
so
is little h.
confused about how the okay, thank you.
Any other questions? Thank you for that, because I hadn't really explained the mirror method. You just have to make sure that you are seeing the or if you don't see the top of it, whatever you do see, let's say that we like saw up to there, that's now your similar triangle. So this distance might get shorter, and if this distance stayed the same, then that would just get short, like it'll be manipulated depending on what happened. Yeah.
On the homework, it says to name the postulate or theorem you used. So for the, if we, never mind.
You good? And then, so by the way, when you text me and it has a picture in it, it goes straight to my email. You need to text me first, like without a picture, because you texted me last night, right? Carmen? Oh, Rhea. Okay, sorry. I swear maybe it was one of my 7th graders, and I'm just mixing up the email. But so Rhea texted me about the homework, and it said write the similarity statement or something like that. What it's asking you to do is put them in the right order. So like the triangle order of like A, B, C to D, E, F, because A goes to D, B goes to E, C goes to F, that sort of thing. So you couldn't say A, B, C, F, D, E or something, you know what I mean? Are we good on 6-3? Wunderbar. 6-4.
What?
Wunderbar. Wonderful. German.
Excuse you?
It's also a Wonder Bar is also like a snack. Anyone want to pass these out? Because I got to run and grab something off the printer really quick. Anybody? BRB, as the kids say these days.
We should get a cricket sound effect whenever he asks if you're a question.
What do we say these days?
I didn't realize that I'm not
No, I say bird to my mom.
Why?
Even though that means bird. If you don't say, you have to add an extra Y when you say yeah.
I'm not.
Spell it G-Y. Yeah. That's depression.
Oh, thanks.
Depression.
Really?
Wait, what? No, I said something
He's
like,
like, I don't care what you
I'm
say.
never
You, I'm going.
Think about that time.
So, similarity in right triangles gets mildly dangerous. And I say that because by dangerous, I mean it's very easy to make a mistake by what sides we relate to each other. So, huh? Today's the 20th, yep. All day long. So the most important thing that you need to like double, triple, quadruple check yourself on is, am I relating the correct sides to each other? And this is why I'm so cautious about this. I wish I had 175. Our homework and a lot of what we're doing here is going to come out of where you see one right triangle with 2 right triangles inside of it. So I've got my one big right triangle there, ABC. But I've got my smaller right triangles, ADC and BDC. So if I'm setting up a relationship statement, I need to make sure that the smallest side on each of them is what corresponds to each other, the middle side on each of them, and then the longest side on each of them, which people will write in the wrong order. It's really easy to goof up. I've seen some of the strongest math students just put things in the wrong order and do the same mistakes kind of over and over again, which gets frustrating. So be careful with your order. They've got your orders given to you here. It's probably more clear on your paper than it is up here. So this is where we start to relate that. AD is the shortest side of my smallest triangle. So if I'm going to relate that to something, it has to be related to the shortest side. So I can either choose CD, which is the shortest side of my medium-sized triangle, or I could choose, what other side would be an option there? Yeah.
AC
AC, which is the shortest side.
of the largest.
Mm-hmm. And what is really dangerous here is when you set up these proportions or these ratios, if I used AD and AC, they'd both be in the same triangle, except I'd be looking at AD as the short side here, and then AC as a short side, not as a hypotenuse. So that's where this gets complicated, because if I could set up here AD in ratio with AC, and that ratio should be the same as this ratio. So that's like, you just have to be careful when you set these up. Again, means extremes theorem. So make sure that when you set up proportions equal to each other, they do agree. If they don't agree, you set something up incorrectly. So there's just an example there. And then this is just basically the same thing. It's the corollary. So setting up a different proportion using different sections. So refer back to these as we need them. But identifying our similar triangles here. So YW is the altitude to the hypotenuse of the right triangle. By the way, we know that that's an altitude because technically, what does hypotenuse mean? What does hype mean? HYP. Do you remember from last year?
Did we learn this?
Over.
Yeah.
Is it over?
Yeah, you guys
It's not over, it's under.
Under.
Oh, it's like hypodermic.
Hypothermia. So the hypotenuse or hypotenuse means under the right angle. So when a right triangle is drawn correctly, the hypotenuse is actually on the ground, like on the bottom, and the right angle is kind of pointing up. So this is the altitude, because if the hypotenuse was flipped down to the ground, this would be standing straight up and down. Does that make sense? Okay, that's why that is our altitude. So we then can set up our three similar triangles. This is where the order is vitally important. So when you're writing these similarity statements, pay attention to your order. If I have X, Y, Z, that's my big triangle, and I'm going short to medium. So I know that these better go short to medium, and I can check that WYZ. Well, WYZ is my middle triangle, so short, YW short, WZ medium, or middle length, we're good. XW, that's my short, to my WY, which is my middle, and I never use my hypotenuse. Does what I'm saying make sense? Like, I don't know if I'm communicating this well. Just the order of checking which triangle am I looking at. And this is where highlighting would be really beneficial. So I'm going to highlight a bunch as we go through our lesson. So here, let's write out our similarity statement relating the one triangle to the other to the other. So if we start, let's all start with the same one. Do you want to start with the biggest or the smallest? Biggest one? Sure. So let's do you want to do PQR? So with how we set this up, I travel my short leg, and then I travel my hypotenuse. So who can give me a next triangle to go in here? I really need to get these out. All right, last one, Calvin, while I get these shuffled. SPR, so you chose this triangle. So you started at your right angle, took your short leg, and then took the hypotenuse. And my last triangle that I would put there, Megan. SQP. Start at my right angle, take my short leg, take my hypotenuse, come back. Perfect. Any questions on why we did the order we did? You want each of these to have short leg, then hypotenuse. Or whatever, however you set it up, you could have started differently, and then each of these would be differently. Be different. All right. So we've done geometric mean before, but here's where people look at a problem and they're like, this is impossible, I can't solve it. When you relate two triangles that both share a common unknown value, set up a proportion so their unknown values are diagonal to each other. So I put this problem here as an example to you of how that then works out. If I have common variables diagonal to each other, I end up with that variable value squared equal to the other product, which comes in handy. Well, okay, so let's do 4 and 18 really quick. So geometric mean, that means 4 and 18 will be my extremes. So your extremes are on top left, bottom right, so go ahead and set up your proportion. From there, we're going to cross multiply. 4 times 18. What's 4 times 10?
40.
4 times 8?
32.
32.
Yeah.
72.
Can 72 be broken up to have a perfect square?
No.
No.
Yeah.
No.
How? 9.
You said it weirdly.
Yeah, sorry. If you said yes, I swear it sounded like it came from Megan. 9 times what?
9 times 8.
Which, as long as this is multiplication, I can pull one of these values out by taking its square root, and I get 3 radical 8. Technically, it'd be positive or negative, but since we're going to be talking about lengths, we only care about the positives.
Can't you
There's
simplify that more?
Yeah, can't you simplify that more? 4 and 2.
Yeah. Well, the 4 and 8.
So the 9 wasn't actually the biggest one here, was it?
Right.
What could we have used here?
36.
Which becomes
6.
radical.
2.
So we could have simplified this further, or we could have thought harder here, or honestly, if you leave it here, I don't really like. You did the manipulation, you just didn't think of the largest perfect square. So I wouldn't really count this as wrong. I would just probably notate, keep going. Ethan? So this is the fancy schmancy way to find the average between 4 and 18. If I asked you average, what is mean? Mean is average, right? So if I told you average 4 and 18, forget about math 2, how would you average? Add them together and divide by 2. So if I add those together, I get 22, and if I divide by 2, I get 11. So this is not exactly the same, right? This is dealing with, if I have two triangles, can I show one more example problem and then see if you still have issues?
Yeah.
Okay. The reason we're doing this is to solve for an unknown length that is shared between two triangles. So this x would be a leg or hypotenuse or something of two different triangles. It's a shared side. So when we come down here, and this problem's done out for you, so it can hopefully make sense. So we want to find the value of y. Y is a shared side. it can either be the middle side of my smallest triangle. It could be the shortest side of my middle triangle, and I can't use it in my biggest triangle. So I have two options. I either use it on my smallest triangle or on my middle triangle. Which triangle do they decide to use? If they use the 4 with the y.
Small.
The small one, right? Because the small one has the 4. We have options here. We could have started either way, but once I start, that tells me I need to have the shortest leg on top and my long leg on bottom. So this has to be the other triangle that uses the value of y. Unfortunately, the shortest leg is its y, and its longest leg is the 12. So do you understand how we set up this proportion? Don't go beyond the blue line, but do you understand how we got to the blue line?
Not quite.
Okay, what's not making sense? I know that this is difficult, so understand, like, I'm right there with you guys. When I first taught this, I was like, huh? Because this was not in, at least we learned it differently. So this might help, Ethan. Forget about the big right triangle. Think about having two right triangles labeled C, D, A, with this as y, this as 4, and this as 8. And then another right triangle that is B, D, C. Sorry, there's no word good for that. That's 12. This is y. And we don't know the hypotenuse, but we don't need to. So I'm going, forget about this. I'm going to relate these two triangles because I've been told these are similar. Right triangles inside of right triangles are similar. We can go back and there's a mathematical proof that has no counterexample. You can try your darndest. There's no counterexample. This always works. So what we're really doing is just relating. If I have two sides that I know, not that I like know their number, but that I can represent, that I can compare to two sides that I know on the other triangle, I can set up these ratios that should be equal because they're similar. So, however, the y compares to the 12 and the 4 compares to the y, or however the y compares to the 4 and the 12 compares to the y, those ratios have to be the same. Because as Calvin brought up yesterday, I can relate triangle to triangle or part to part and then part to part. So we set up here part to part, or actually this could be either. This could be part to part and then part to part, or triangle to triangle, triangle to triangle. So this actually could be either. Just check it out. 4 relates to the y, just like y relates to the 12. Or 4 relates to the y, like y relates to the 12. Does setting up this proportion make more sense now?
Yeah.
Okay. So now, this is totally worth copying before I forget about that. Now we want to solve. Any proportion, we can cross multiply, solve for our variable to get our value. So we cross multiply it and get that my y squared equals 48. I then square root, and I simplify if there's any perfect square inside of here. So they actually look at this as being radical 16 times 3. Then the 16 is a perfect square, so we can pull that out, and we get 4 radical 3. And I can go back and I can check the Pythagorean Theorem and do a squared plus b squared and get my c squared. A squared plus b squared and get my c squared. But this value squared would just be 48. So sometimes leaving it as radical 48 would be fine, because it'd be easy that way. Yeah?
What's the significance of AC being x equals 8?
There isn't. It's just a side they give to you.
Excuse the interruption. Could I have Josh Malik to the office, please? Josh?
So I think x, I think I gave you guys solutions on this. Oh, we do it down here. We have to solve for x first, and then we can solve for y. Because you have to do your x before you can do your y.
Okay. So you put that in.
Yeah, I gave it to you on this one to make it easy.
Okay.
Because I know that there's that moment of, I don't understand everything that's happening, I just want to be able to understand a little bit that's happening.
I didn't get why it was highlighted, and then I didn't get why if we're supposed to solve for x that it's
Yeah,
always-
I gave you like all of step 1 done. Does, Ethan?
I'm kind of confused on when to use geometric means.
So we use this when we have an unknown value shared between two triangles. That's when we set up this proportion and set those unknowns diagonal to each other. When it's unknown shared to two triangles. So Ethan, if this was my y side, it's my long leg of my big triangle, or it's the hypotenuse of my middle triangle. So again, I could solve that setting up those ratios, but it would be different since it would then be the long side and the hypotenuse as opposed to long leg and short leg is what it is right here. It's a leg on both triangles. Can we move on and do the next one? Because the next one is where it really gets nitty gritty. There's a couple things that I drew that weren't on there. So we need to solve for x and y. How can we solve for x? Emma?
4 over x equals x over y.
How? So when you say 4 over x, what are you relating?
The short side of the triangle on the left. And the x.
So like short leg and hypotenuse. So I'm going to say short leg, hypotenuse. So when I relate that, it's going to have to be short leg and hypotenuse. So you use,
X over y.
yeah, which triangle then are you looking at?
The big.
The big triangle. To make your x, you now know x has to be here to use the geometric mean. They have to be diagonal. So I need that to be my short leg. So you could just put x there and then figure out what triangle is that I'm working with to be the short leg. That must be the big triangle. So then it's related to 9. Ethan? Or that answers it. So then we get x squared equals 36 and x equals 6. So that one is easier to solve. The y, the altitude tends to be a bit more difficult, or comes out to be a radical value. What proportion, somebody I haven't heard from yet today, can I set up to solve for y? Actually, let me use green. Okay.
So then you go 4 over y equals y over 5.
Excuse the interruption. Could I please have Ty Hunt to the office? Ty?
So we know the y has to be on top. So right now what we set up, it's a little hard to see, but it looks like short leg, long leg. Like the 4 looks to be our shorter leg. So if I have short leg, long leg, I need short leg, long leg. So if I'm using y as a leg, it's got to be this triangle. So yeah. So then y squared equals 20, and y, when reduced out, anyone know it? Calvin?
2 radical 5.
Thanks. Because this would be square root of 20, which becomes square root of 4 times 5, which I can bring out the 4 and make it a 2. Questions on this? I know this is challenging. I gave you the easy form of the homework. We're going to take questions tomorrow.
Wait, is this the last topic in?
No.
Oh.
But this is a good point to pause and take, because this lesson is pretty if you don't struggle on the homework a little bit at least, I'll be surprised. Because this is just not easy work. We're getting into that deep math that takes a lot of focus and concentration. Caleb?
Oh no, I was just stretching.
Oh, okay. Your stretch looks an awful lot like you have a question.
You can touch the top of that rock.
So,
Push down. I probably can try.
this is a really cool problem. So if you take your notes page and fold it down the diagonal, and then fold the altitude of you don't need to, but I'm saying if you take any rectangle, we can make this shape that we see here. Because we know we have right angles in all the corners, we know this diagonal, then I can create a 90-degree off of that. I'll zoom out so you can see everything. So it says, one triangle, draw the altitude from the right to the left. Number of the angles are shown, cut out the 3 triangles. Can you match the angles of the triangles to show that all 3 triangles are similar? And then, theoretically, this is easy to say, could these 2 triangles fit into the bigger triangle? Yeah, right? How would we match up angles to prove similarity based off angle? If I start in my rectangle here, what relationships would we start to say or start to make? If I look at angle 7, what could angle 7 be equal to? Megan?
Angle 3.
Why?
Because they're
Alternate interior, right? Angle 1. Yeah.
Angle 4.
Angle 4. I'm trying to reason through this again. Ooh, I have another relationship actually. Does anyone recognize anything? Anything else that we can see? So what I'm looking at now is 1 equals 4 because alternate interiors. But what else would 4 equal based off the 2 smaller triangles that we see? Megan?
6.
Why? I love it.
Because the 2 triangles within the big triangle are similar, and it's the one on the short side that is at the 90-degree angle.
Okay, I like it. The other relationship we can see, 4 and 5 have to be complementary because they're the other 2 angles. 5 and 6 have to be complementary. So if 4 plus 5 is 90 and 5 plus 6 is 90, by substitution, 4 and 6 must be congruent. Emma?
Which means that 5 is also congruent to 7.
Which means that 5 is also congruent to 7, which then is also congruent to 3. And from there, we would be able to show that those triangles are similar. And once we see the similarity, we can then match up and set up those ratios. Any questions on this? So I hope that as we do more of this, you're getting better at looking at things at different directions. Like when we made this jump to involve angle 6 or involve angle 5, you can't just get stuck looking based off the parallel lines. You got to relate these angles using all these theorems that we've got floating around in our head. Any other big questions from this? All right. We got a couple minutes. You want to go ahead and start? What's up? We are going to take questions from this tomorrow. This is the lesser of the 2 homeworks. I know there's still a decent amount of problems. Just be careful how you set it up, and all will be fine. I would say watch through the video if you can. I'll have it uploaded hopefully by 2-ish. And then let me know. We will take questions on this homework tomorrow, but that means that you need to attempt it before you come to class. So please try to do this tonight.
Yeah, and now look who has a stack.
You guys want to do a couple of these?
Sure.
I'm gonna no.
What's a segment of the hypotenuse?
What are you looking at?
Abuse.
Like, so like RY is a segment of the hypotenuse, or XR is a segment of the hypotenuse. So if it's triangle XYZ, that's the big triangle. So the segments of the hypotenuse are XR and RY. Because those are what make up. So this is asking in the big triangle. In triangle XYZ. Identify the hypotenuse. Well, the hypotenuse is XY. But the segments of it are X,
I was going crazy, sorry.
XR, and RY.
Yeah.
Because really what that is one of them is going to be your short leg on the short or the small triangle, and the other is your middle leg on the middle triangle.
Yeah.
So XR is the middle leg on your middle triangle, RY is the short leg on your small triangle.
I was going crazy, sorry.
All right, on that, we are out of time, so please head on back to your 8th grade peeps, and I will catch you guys tomorrow. Please encourage your parents to help with the yard sale. We still need volunteers. We're doing pickups tonight and tomorrow. We really, really need people to help price and sort.